Hello again, and welcome to part two of this lecture on the mammalian heart. And so what we're going to do in this case is talk more specifically about the structure and function of the mammalian heart. So let's begin by considering where it's located, first of all. Maybe that's not a big surprise. Most of us know where it's to be found. But you can think of it as this cone-shaped, hollow, muscular structure. It's hollow because it's, consists of chambers and vessels located in what's known as the thoracic cavity. So you can see here in this bull, for example, it's there in the just anterior, just north, if you look towards the head end of the sacculated stomach, which is right behind it and separated from the heart by the diaphragm itself. And that's the same arrangement we have in terms of our heart being located in the thorax or thoracic cavity, separated from the abdomen by the muscular diaphragm. That's important for breathing, of course, regulating breathing. So we can also think about the apex of the heart here being pointing dorsally, or pointing, not dorsally, pointing towards posteriorly towards the rear end, as it were, of this animal here. Now, one of the things that's interesting about having the proximity, in this case, of the heart to the sacculated stomach, particularly the part of it that's called the reticulum. This is in a bull or in a cow. What can happen is that, well, I'll talk about this in a little bit more, but they can ingest things that can actually penetrate and get and injure the heart. But let me come around to that in just another couple of slides. I want to just stick with the location of the heart for a second. You don't have to remember the term here, but just to kind of recognize that the heart, this is the front of the person. Here again, this is a cross section through the thorax. There's the front or the anterior portion or the posterior portion of a person. Let's say in this case, and you can see the heart's right in the middle in this space called technically the mediastinum, and surrounded really by the lungs. A point that I'll come back to when we watch the dissection video. So this kind of tells you where you are located. It's pretty much in the middle. We tend to think of it as being somewhat on the left, but most of the heart is actually right smack in the middle in this mediastinal space. One thing that's important is that it's surrounded by a tough fibrous sac known as the pericardium. It's literally suspended in this membrane, this sac. It's got a little bit of fluid in it, and that's important because the little bit of fluid that surrounds the heart, because it's sitting in this fluid-filled sac, not a lot of fluid, but just a little bit, because the heart's constantly moving, right? It's constantly pumping, constantly moving. And so this gives it some lubrication for all this movement that goes on for many years, basically. So that's a great mechanism. So here again, we're talking about, if you look at the bottom here, we're talking about this sac here. This is called the pericardium. It's this fibrous sac that the heart embryologically slides into, basically. It's pushed into, and it has just a little bit of fluid inside there. Now, there is a condition called pericarditis, which means literally inflammation of this membranous sac, and you can get excess fluid buildup in the cavity, and that can get quite dangerous because it can actually compress the heart and interfere with its pumping functions. And this is what I wanted to come back to now with regard to, in this case, the bovine thorax here. You see the heart again, and it's very close to this portion of the sacculated stomach called the reticulum. Sometimes cows will ingest sharp objects just by accident, and they can get pushed through the diaphragm and penetrate the pericardial sac and suffer from pericarditis. So this is kind of a risk factor for them because they have this huge rumen here, this huge sacculated stomach, I should say, that brings the heart into close proximity to food that's ingested, and that can be a problem. All right, well, let's think about how the heart is structured and its function, and particularly what we want to do is trace the flow of blood through the heart. This is something, of course, that I'll be demonstrating in the dissection video separately, so I want to make sure that we understand some of the principles before you watch the dissection video, and that's hopefully something we can accomplish here. So think of the heart as really two side-by-side pumps. You have the right side and you have the left side. You think of the right side of the heart as the pulmonary circuit, and the left side as the systemic circuit. And that should be clear already from some of the things we've been talking about. So we're kind of repeating some of the information that hopefully will help you to become more well acquainted with it. So we're basically talking again about oxygen poor, carbon dioxide rich blood coming into the right side of the heart, getting pushed into the lungs, getting oxygenated, all this good gas exchange happens, comes back into the left side of the heart, and then gets pushed out to the rest of the body. Right? So both sides pump at the same time. That is the right side of the heart and the left side of the heart. One side pumping blood into the lungs, the other side pumping blood, the left side pumping blood out into the body. It should be evident as well that what we're talking about in terms of the mammalian heart is a four-chambered heart. So the right side has two chambers. It has a right atrium and a right ventricle, and the left side has a left atrium and the left ventricle. The atria sit on top of the ventricles, as is pictured here, and this just shows how blood comes in through the venous circulation into the right atrium, gets pushed, the atrium contracts, it gets pushed into the right ventricle, and that pumps blood into the lungs, and then comes back from the lungs here into the left atrium, gets pushed, the atrium contracts, pushes blood into the left ventricle, and that then pushes the blood back out into the systemic circulation through the aorta, which you can see pictured here. This is a bit more of a detailed presentation, and you'll see this very clearly too in the dissection of the heart. That's the last video that you'll watch. But here, what's shown here are some of the valves, and they're very important in terms of separating or controlling, I should say, blood flow throughout the heart. So for example, what you can see here is that when blood comes into the right side of the heart, into the right atrium, and then the atrium contracts and pushes the blood into the right ventricle, you have what's called a tricuspid valve. So sort of three flaps to this valve. But the valves have these little chordae tendineae. They're like strings attached to the flaps of the valve. They're attached to little projections of heart muscle here called papillary muscles. And why do you have this? And the same thing over here. This is a bicuspid, a two-flap valve, if you like, on the left side of the heart, but the same arrangement with this chordae tendineae and the papillary muscles here. So what's the function of that? Well, basically because the ventricles contract very forcefully, especially the left ventricle, you don't want these valves here to allow any blood to flow back. When the right ventricle contracts, you want no blood flowing back into this atrium, into the right atrium. We want to make sure that all the blood flows out to the lung through this pulmonary artery here. Okay, that's important. Likewise, you don't want any blood coming backflow, as it were, from the pulmonary artery into the ventricle. And so you have a valve here, what's called a semilunar valve, that you kind of see, look at the shape of this, as when blood gets pushed up into the pulmonary artery, it will close this valve here so that it can't flow back into the right ventricle. And likewise here, you have an aortic valve that prevents blood flow, backflow from the aorta when the left ventricle contracts. And likewise, the mitral valve here, the bicuspid valve, prevents blood from flowing back into the left atrium when the left ventricle contracts. So these valvular arrangements are crucial to making sure that the blood stays well separated in the different chambers of the heart, and there's no backflow from the vessels that either come into the heart or leave the heart. Let's think about the major vessels. Arteries are best regarded or defined as channels, vessels that take blood away from the heart. They're not necessarily always oxygenated. Right? The exception, for example, is the pulmonary artery, which is an artery, carries blood away from the heart to the lungs, but it actually has deoxygenated blood in it. Okay, so that's an important point to remember. Likewise, the blood coming in veins, in this case, bring blood back to the heart. It's important again because pulmonary veins carry oxygenated blood from the lungs back to the heart. So don't confuse arteries with always being oxygenated, having oxygenated blood, and veins always having deoxygenated blood. Just think about them as one carrying blood away from the heart and the other is carrying blood to the heart. Okay, so these are the major vessels. I've already mentioned them. You have these large vena cava, as they're called, that bring blood to the heart, one from the head and neck and the limbs, upper limbs, and the other from the rest of the body coming in from below, both of them coming into the right atrium. And then you have, as I've mentioned, the pulmonary artery that carries blood into the lungs. Coming back from the lungs, you have the big pulmonary veins. And then, of course, the aorta carries blood away from the left ventricle. So here's kind of a nice view of the heart with some of the vessels, the major vessels that we've been talking about. What I want to point to here is that the heart muscle itself needs blood supply. And what's nicely shown here are the coronary arteries and coronary veins. Okay? Coronary arteries, of course, are crucial in particular because they carry blood to the heart muscle. And if those become plugged up or occluded, as it were, with fatty deposits or something of that sort, then you have basically what's called a heart attack. The heart can develop necrotic tissue, can cease to function, and you might actually die if these major vessels become plugged. Well, what about blood pressure? How is blood pressure regulated? Because the heart, through the sort of pumping action, as you can imagine, releases blood in bouts, sort of spurts, as it were. So how do you keep blood pressure from bouncing around, from going up and going down? Well, one way in which you do that is through the major arterial system, especially the dorsal aorta, the big, heavy vessel that carries blood away to the whole body. They're very elastic, and they can constrict and they can relax in response to this ventricular ejection, ventricular pushing of blood, this contraction, you kind of smooth it out so that your blood pressure stays constant. That's a simple way to maintain a regular, or even, if you like, blood pressure. Of course, if you've ever had your blood pressure taken, you know that you get sort of a top number and a bottom number. The top number refers to the systolic portion of the reading, and the bottom number, the diastolic reading. The systolic reading is the maximum pressure at ejection, basically when you have ventricular contraction, that gives you that top pressure, and then, or systolic pressure, and then when the heart relaxes, when blood flows into the ventricles, that's the bottom number, the diastolic measurement. That's the pressure during the relaxation of the heart muscle itself. So here's just another review, really just a review slide for you of how blood flows through the heart. I won't repeat all of this, just a review slide. Of course, the video will be posted so you can review this at your leisure. One point we want to make, this might be obvious from what I've said, is that the heavy lifting of the heart muscle is done by the left ventricle. If you look at this slide here, where it's cut through the ventricles, the right ventricle and the left ventricle, you can see how very much more muscular the left ventricle is. Because what does the left ventricle have to do in a mammalian circulatory system? It's got to push blood all the way out through the dorsal aorta here, throughout the whole system. Right? So that's a heavy push, especially in a large animal. So you have to have a really well muscular left ventricle. In comparison, the right ventricle has a relatively thin muscular wall, because all it has to do is push blood through the pulmonary artery into the lung. That's it right here. That's a short distance, so it doesn't need much strength. The key to getting blood out to the whole organism. We mentioned the heart valves a little bit already. You can see the tricuspid. This is, if you're slicing through, a view slicing through the top of the heart, kind of cutting right through it. And you can see here that you'd be looking down on top of the atria, the right atrium here, the left atrium. Remember I mentioned that this is a tricuspid, three-cusped valve that separates the right atrium from the right ventricle, whereas it's a bicuspid or two-cusp valve that separates the left atrium from the left ventricle. Then you have these tricuspid aortic valve and pulmonary valve. So as I've mentioned, these are crucial for making sure that things stay well separated, there's no backflow happening. So you can also see here how, especially in this picture here, how when you have blood in the ventricle, you can see where it's pushing up, when it's pushing up against these cusps of the atrioventricular valve, it closes up. Right? These two things meet in the middle, and that prevents any blood flowing back into the atrium here. So it's critical, and these tendinous fibers, the chordae tendineae, make sure that with all that pressure, especially in the left ventricle, you don't have these flaps simply sort of pushing open into the atrium, eversion of the heart valve that could happen if you didn't have these strings to hold it firmly in place as this powerful contraction of the ventricle happens. Because you can have a situation where you have leaky valves. That can happen. Right? So again, another view of these different valves, tricuspid and bicuspid valve, also known as the mitral valve. Right? Just another view of it. And Um, sometimes, either through some kind of developmental defect or a condition that can be brought on by disease or just aging, these valves, of course, can leak. And you might hear a murmur. Basically, that's blood that's pushing past the valve. You get some backflow, let's say, and then you might need a valve replacement. Different devices that can be used, mechanical devices or biodegradable kind of like pig valve. Pig heart valves are often used and well tolerated as a valve replacement surgery. If the valve gets too leaky, you get too much mixing of oxygenated, say, and deoxygenated blood together, or it's simply not efficient in terms of pushing blood into the lung and keeping it well separated there. You might also wonder what the heart sounds represent. You have that lub-dub noise, as it were, that you can hear through, very plainly through the stethoscope. And that's a sound made by the valves closing. So the atrioventricular valves, when they close, they make that first lub sound. And then when the semilunar valves of the pulmonic, the pulmonary artery and the aorta itself, when they close, that's that dub sound. Right? So that's what it's the valves closing that gives you the lub dub sound that we're so familiar with. Let's just talk for a second about the cardiac cycle here. I've already mentioned systole and diastole, these blood pressure components. So thinking about the cardiac cycle, if you were asking, well, you know, what's your heart rate, for example? How often does it beat per minute? It's defined by the cardiac cycle. And that basically means, as it says here, all the mechanical events associated with blood flow through the heart during one complete heartbeat, okay? Both the systole and the diastole. That's one complete cycle. And so when we talk about heart rate, and this is important because we'll talk about heart rate differences between species in the last section of this lecture, we're talking about really the frequency of cardiac cycles, usually measured in beats per minute, and lots of things that can change that. Physical conditioning, for example, can change the heart rate. Heart responds to exercise, the heart muscle grows in size, and when the heart grows in size, the heartbeat becomes slower. As I might have mentioned, heart muscle contracts automatically, but you don't want to have all these muscle fibers in the heart contracting independently. You need to have a way of getting coordinated muscular contraction. And so you have built into the heart a special electrical system. And it's quite complex. We don't have time to really go into the details of it. And you know, this is something you can find out more about on your own if you're interested in that. But certainly a key part of that system, that electrical system, is what's known as the sinoatrial node that sits at the top of the right atrium in the atrial wall and can be defined as the heart's pacemaker. This is where the pace is set for the heart that gets that coordinated beat going. But you also know that the autonomic nervous system, fibers coming into the heart through the parasympathetic and sympathetic components of the autonomic nervous system, can influence the rate at which the heart beats. So we know that when you get very excited or angry, for example, or fearful about something, that excites the sympathetic nervous system, the arousal system. And so those fibers coming into the heart can then increase the rate at which the heart beats. And likewise, in a more relaxed kind of situation, the parasympathetic part of the autonomic nervous system is active and heart rate actually decreases. And that's what's shown here is there are parts in the medulla, this brainstem portion of the brain, that are these kind of control centers, if you like, that through these sympathetic and parasympathetic components, especially in terms of the vagus nerve that that carries parasympathetic stimulation, it tends to slow the heart rate down. So the heart will beat on its own without these fibers. They simply, that is the sympathetic or parasympathetic fibers, but this kind of innervation is important for regulating the rate of the heartbeat in connection to emotionally arousing or relaxing kinds of stimulation that the organism um, might encounter. All right, so we'll stop it there for this segment, and stay tuned for the last segment, segment 3, with just a few more comments about some comparative aspects.